Miss Hawina. So we'll be looking at the chemistry revision, and if you've done this before, if you've attended this class before, we normally have our house rules, which I will still repeat. If you do have a question, raise up your hand. I'll give you the microphone. Once you're given the microphone, answer the question, or if you want to ask a question and then mute again so that we can have smooth flow. Now, there's a paper that was sent to you. There is a paper that you're going to use in revision. There's a revision class, so just ensure that you don't leave any stone unturned. If there is a question or there's a concept that you don't understand, please ask as we move. So I'll start by sharing the question paper, which I believe you also have. You do have the question paper. Okay. I believe you can see the question paper that is being shared, and let us make this class an interactive class. So you have a question. If I ask a question, please do answer so that we can have an interactive class. Now, let's look at the first question. This one is a typical paper 2 question. You all know how paper 2 questions are set, and at this juncture, I believe that you also know that there's some of the topics that can never miss, even in KCSE paper 2. Something like electrochemistry, the question 1 that we do have, things like organic chemistry. So we have this question 1 here. The table below gives the standard electrode potentials for a number of half reactions. So we do have the half reactions. We have the zinc ions plus electrons to give that. And of course, we have the E value that has already been given there. I want to believe that at least you've gone through the questions. So we can see we have zinc ion, and these ones, of course, in this particular question, we've been given the actual symbols of the elements, meaning we've been given the actual elements. So it's a bit easy. At times in exam, don't always expect the elements, real elements. You'll be given letters, maybe letter B, C, just like that. But in this case, the letters have been given. Anytime we have an electrochemical cell or we have half reactions like this, there are things that we first have to look at. There are things that we need to know. First of all, in this question, which one is the strongest oxidizing agent? Which one is the strongest reducing agent? These are some of the things that we need to know and give a reason as to why, because that is one of the most common questions that is normally asked. Like in this case, we do have the 4 of them. Can someone just tell me which one is the most, or which one is the strongest oxidizing agent? If you know the question, raise up your hand. I can see Melvin, your hand is raised. Yes, Melvin.
AG.
The AG, correct, that is silver. Very correct. And why?
Because it is the most, it has the highest, most positive E note.
That is correct. So we say because it is the most electropositive. Very correct. These are the first things that you need to know. Anytime you're given an electrochemical cell, the one which is the most positive, meaning the one with the highest positive value, is the one which is the strongest oxidizing agent. The strongest oxidizing agent. And then on the same note, which one is the strongest reducing agent? Strongest reducing agent here. Strongest reducing agent. Anyone with an answer? Anyone with an answer? I can see Andrew, your hand is up. Yes, Andrew. Andrew?
Zinc ions.
Very correct. And the oxidizing agent, that is very correct, Andrew. And what is the reason? Reason?
Has the highest negative value.
Correct. It is
As
the
the highest
most
molecular value.
is the most electronegative. Now, I've just asked that question and there is an answer. There are two answers that I've gotten. There is one person I asked which one is the strongest oxidizing agent. Which one is the strongest reducing agent? Now, we do have ions and we also have the elements or the metals themselves. So if you're asked about the oxidizing agent, reducing agent, we don't talk about the ion. We talk about the agent itself, which is in solid state. Just like when I asked about the strongest oxidizing agent, I was just given the silver. That is very correct. In the strongest reducing agent in this case, it is also very correct, but you give it as zinc, this one which is in solid state, because the agent is not an ion. And the reason is because it is the most electronegative. So the one that is the most electronegative, actually you'll realize that it is the one that is most reactive, is the one that is the strongest reducing agent. And the one that is the most electropositive is the one that is the strongest oxidizing agent. Now, still on that question, I've not started looking at the questions that we do have, but I'm looking at the questions that are normally or commonly set when it comes to these half reactions. You can be asked a question which is almost similar to question 1, but a very commonly set question that identify two electrochemical cells that will give the highest EMF when combined. I'm repeating that question. Identify two electrochemical cells. Identify two electrochemical cells that will give you the highest EMF when combined. I can see Quincy.
Okay, you'll pick that one for negative 0.76 and positive 0.80.
That is very correct. Very correct. Thank you for that. And the way he has said it is very correct because in this case, you've been asked about the electrochemical cell. So if you are to give the answer, you will write the whole of this reaction. You'll write the whole of that reaction. The whole of that reaction is an electrochemical cell. Unless you want to write something like zinc stroke zinc 2 plus something like that. But then what he has said is very correct. What will give you the highest EMF is a combination between the most electropositive and the most electronegative. That is what will give you the highest and a very, very commonly set question. Now, let's now look at this question that we do have here. Draw an electrochemical cell for the reaction that will give. Now, this one is not the most, but the least. My first question is, if you look at these, the way they are, looking at the A values, and remember, if you're talking about this, an electrochemical cell is a cell that comprises of two, we must have those two salts. So you must give a combination of the two salts. So if I ask first of all, because we need to know, if you're to draw the electrochemical cell, you need to know which salts that you'll be talking about here. Which salts are you going to draw here? Now, among these four, which two will you combine to get the least EMF? Somebody's hand is already up. Always Melvin. Other people, where are you? Melvin, start us off. Yes.
That for iron and copper.
He's saying iron and copper. Correct. Good trial. Another person who can try. Who else can try? The ones that will give the least EMF when combined. And how do you know the ones that will give you the least EMF when combined? How will you know that? If we were to take this one for copper, the one that he has said, copper and iron, copper and iron. If you are to take the one for copper and iron, what will be the EMF? I'm giving you just 1 minute. If you can calculate that, 1 minute. Joseph, your hand is up. Joseph? Yes, Joseph, we can hear
Can you hear me?
Yes, we can hear
Okay,
you.
I wanted to answer the one for the least EMF first.
Yes.
I think it's the silver and the copper.
Silver and copper. Silver and copper, very correct. I think I like the discussion, silver, copper. Somebody's hand is still up. There are some others also. We do have someone calling himself KSA. Yes, KSA. KSA, your hand is up. Is not giving an answer. Now, let us look at what we need. Like, for example, when I asked about the one that will give the highest EMF, we're looking at the one that is the most electropositive and the one that is the most electronegative. In this particular case, we want the one that will give the least EMF. Look at two of these electrochemical cells that have been given, which their E values are close to each other. The E values are close. The E values are close. Look at from zinc to copper, the four of them. Which two have E values that are almost close? That is what will give you the least EMF. That is how you will identify. Just identify two values that are almost close. And by the way, even the answers that you've all given, we can as well work out the EMFs and then we see which one is correct. So just look, I'm just giving a clue of how we'll give this answer here. Just check the four of them and see which two have EMF values that are almost close to each other. That is the ones that are close to each other, the ones that will give you the least EMF. Mark, your hand is up. Please, if your hand is up, if I give you a microphone, let us not waste time. Yes, Mark?
I think it is zinc and iron.
Zinc and iron. Any other person? Any other person with something to say? Any other person with something to say? Dominic?
Cha.
Yes.
And what if you are asked about the reason why we have chosen the two?
We've chosen?
The two zinc and the iron.
The two zinc and iron. Of course.
Yes.
Now, actually the answer is zinc and iron. And I've just said they have the closest EMF. The E value. The E value is close. The E value of zinc and the E value of iron, they're close. And that is what will give you the least EMF. So that is something that you're supposed to know. If you are asked about the highest EMF, look at most electronegative, most electropositive. But if it is the least EMF, don't even look at positive and negative. Just look at the two values that have E values which are close to each other. Like in this case, the way somebody has given us an answer, yes, very correct. If you look at zinc and iron, these two, the combination of the two will give us the least EMF. Just giving one last chance to Quincy. Yes, Quincy.
Could you please elaborate this statement that I would make?
Yes.
When told to select two elements that give you the least workable EMF, arrange the elements in ascending order, then pick the two that give the lowest positive EMF. What does it mean?
First of all, you've been told to identify them.
When told
Like
to
these
select
ones,
two elements.
so let us, using that your question, we are working, let us assume we are working with what we have here.
Mm-hmm.
Yes, so the first question is select.
Two elements which
will give?
To the least workable EMF.
least workable EMF, like in this case, we've given the, and remember your question is elements. So the elements here, ion, yes?
Then you're supposed to arrange the elements in ascending order.
The two elements that you've selected in
Yes.
ascending order, meaning from least to highest.
To highest.
I think that, see that one you can select using 0.7, negative 0.76 and negative 0.4. Which one is the largest here?
For the ion.
The ion, correct, negative 0.44. Then the next
Yes.
question was?
You pick them, then you give, then will it give you the lowest positive EMF?
Yes. And I think that is a question that I think it's here. We are going to calculate and see the least EMF. It will give us it should give us the least positive EMF. It should give us the least positive. Thank you for that. So let's continue. Thank you. So we've identified the two, zinc and iron, because they have E values that are close to each other. So we are supposed to draw an electrochemical cell. This is something that you're supposed to draw on your end. Maybe I'll give you a minute, but first of all, let us identify what are some of the things that you're supposed to look at when you're drawing an electrochemical cell. Remember, an electrochemical cell, just as I've said, is a combination of these two cells. We do have the two half cells. They are combined. So we'll have one cell this side. I will give a complete drawing, and another cell this side. Inside these cells, first of all, one is on the left-hand side, another one is on the right-hand side. They are just not put randomly like that. You have to select which one should be on the left-hand side and which one should be on the right-hand side. The left-hand side is normally the anode. I'm repeating. The left-hand side is normally the anode, and that is where loss of electrons take place. And loss of electrons take place at the anode, and it takes place at the anode where the most reactive metal is. So we do have the left-hand side and the right-hand side. Left-hand side, I've said, is the anode. And the left-hand side, which is the anode, that is where the most reactive element is placed. Then we do have the right-hand side. The right-hand side, if you're drawing the two, so you'll have one cell here. I've said I'll give the complete drawing. Then you'll have the other one, this other side, which is now the right-hand side. The right-hand side, that is where you're now going to have the cathode. The cathode is where we now have the gain of electrons. Remember, electrons lost at the anode are gained at the cathode. So the electrons must first of all be lost at the left-hand side, and then they are now gained at the right-hand side of the cathode. So the left-hand side consists of more, or the more reactive metal, and the right-hand side consists of the least reactive metal, if you are now comparing the two. Now, another thing that you must have also is the electrolyte that is being used. Remember, there are standard conditions for any electrochemical cell. First of all the solutions should be in 1 molar. Another thing, the temperature should always be room temperature, and the pressure also at 1 atmosphere. Temperature of around 25 degrees. So those are standard conditions that we need to know when drawing a half cell, or at times you can be asked. There's a certain case you see that asks such thing. The standard conditions for an electrochemical cell, the electrolyte should be 1 molar of that particular solution or salt that you're using. And then the temperature should always be maintained at 25 degrees Celsius, and then a temperature of 1 atmosphere. So when you're drawing that, we do have zinc and we have iron. I've explained what should be where. Cathode, anode. Look at iron. Which one should be on the left-hand side and which one should be on the right-hand side? Somebody. So that I give 1 minute, everybody should come up with a good diagram. We need to know, first of all, how the diagram should be. The diagram consists of two half cells. One half cell will have zinc, another half cell will have iron. But these two half cells are not just placed anyhow. There's one that should be placed on the right-hand side, another one on the left-hand side. Now my question is, I do have zinc and iron. Which one will be on the left-hand side? Which one will be on the right-hand side? I can see, Ryan, your hand was up first. Yes?
Zinc should be on the left hand side and iron on the right hand side.
Very correct. Zinc on the left-hand side, iron on the right-hand side. Because if you look at even if you look at the E values, you realize that zinc is more more reactive as compared to iron. And we've said that the one that is more reactive should be on the left-hand side, which is the anode. Now, these two half cells are connected. Remember, we're using the half cells to calculate the E value. So these two half cells are connected using what? You don't need to think about that. How will you connect the two? Somebody give me an answer. How will you connect the two? Quickly. How will you connect the two half cells? How do you connect the two half cells? Yes, Joseph.
Using a salt bridge.
Very correct. Using a salt bridge, and the salt bridge is made of what? Salt bridge is made of what? Anyone with an answer? Salt bridge is made of what? Yes, Victor?
Potassium nitrate.
Correct. Can use potassium nitrate because the salt bridge should not react with any the solutions that are being used. So I'm giving 1 minute. Draw here, and remember, these elements are, or these ions are dipped. These rods, which are the electrodes, are dipped in solution of their own ions. So if you're drawing your zinc this other side, the zinc should be electrode, and that electrode is dipped in 1 molar solution of zinc ions. The same side, on the right-hand side, you're going to have ion, anode, sorry, not the anode, but the cathode. The electrode is the ion, and then dipped in 1 molar solution. Quickly, just a minute. Draw that, and then we'll look at, then you'll compare with the one that I'm going to give here. So just 1 minute. At the same time, if you do have a question, you can ask. If you have a challenge drawing, these are very commonly set questions. You'll always be asked to draw. So the key things I've highlighted. Even as you're drawing, as I'm continuing to make the comments, you can continue to draw. The comments at least are helping you to know. Ensure that most reactive is on the left-hand side. The left-hand side is where we have the anode. At the anode is where we have the loss of electrons. Then the one that is least reactive, if you're comparing the two, should be on the right-hand side. That is what you're drawing. Then they're connected using a salt bridge. Somebody's hand is up. I've given you the microphone. Your hand is up, yes. Chezidek, or yeah, a name like that. So I want to believe that at least you have a diagram, because drawing might be a bit challenging for me. Here, let me just give what we are supposed to have. You should have something like this. But ensure that you have your diagram in check. There are some things that are missing here. Most especially what is missing here is this one here. You should have 1 molar. So just before the iron 2 ions here, there should be 1 M. Also here before the zinc 2 ions, there should be 1 M to represent the 2. Another thing that I would like to mention note on this, unless there is a question here. I think I'm done with this, unless there's a question here. So ensure that your diagram is something like this, but modify it so that you can have 1 molar of iron to ions. Also here, 1 molar of zinc to ions. And then zinc dipped in the solution. Iron rods dipped also into its solution. Another thing that I wanted to mention is something that, at least because this is a revision class, I can just mention it here. Something that you've been doing in class. Remember, in this particular case, if you look at whatever we have, like the questions that we have, the results that we do have here after these half equations, all of them are in solid state. They're in solid state. The states are very, very important. For example, if at all we were drawing, just an example, if at all we were drawing an electrochemical cell for something like zinc and bromine, I'm giving a very important concept. If we were to give an electrochemical cell between zinc and bromine, remember, bromine at room temperature is a liquid, not a gas. It's a liquid. Now, if at all we were having a liquid here, we can't have an electrode, which is we can't have bromine liquid as an electrode. At that particular point, it means, like in this case, zinc will still be where it is, because of course the reactivity series, we've talked about that. And then on this other side, the right-hand side, this is where we are going to collect now the bromine, but this bromine is now in liquid. How do we collect in liquid state? In liquid state, we'll not have an electrode here. But since we want to collect the product, which is in liquid state, that is where we introduce the platinum electrode. We now introduce an inert electrode. And the inert electrode that we do have is platinum electrode. But then this electrode itself must be dipped in what we now have. Remember, we want to collect a solution. So this solution will be collected. So where we have this iron rod here, if you see that iron rod, we are going to, instead of that iron rod, we are going to have a platinum electrode being used. But then that platinum electrode, at the same time, we're going to have a porous plug. That porous plug is where the liquid is going to be collected. The porous plug, that is where the liquid is going to be collected. So always know, if at all it is just solid, correct the way it is. If we do have a solid and then whatever is being collected in this particular case is a liquid, we must have a porous plug. The porous plug or the porous plug is what is going to collect that liquid. And then we are going to use an inert electrode in this particular case. Platinum electrode can be used. Another case scenario is when the product being collected is a gas. For example, we have hydrogen gas. Also, we can't use an electrode which is in solid state because we are collecting a gas. So that is where the diagram of gas collection somewhere here at this particular point is also being used with a platinum electrode. So I was just mentioning those ones. I believe that they were mentioned in class as you are doing the topic. Unless there is a question up to that point, I beg to continue to the next question. Thank you. If there's no question, let's proceed. So that is the diagram. I've talked about the diagram. Let us look at the EMF of the cell. And when looking at the EMF, the easiest way we talk about, this one is normally treated as the left-hand side, this one the right-hand side. So EMF, you can use it in terms of left-hand side, right-hand side. And then you say EMF, that is the E value, is E right-hand side minus E left-hand side, just something like that. Or cathode, or the E cell can be cathode and anode. Unless, yeah. I'm just giving you a minute to calculate that, because I want to believe that at least you have the answer there. Then compare your answer with what I do have. You can compare your answer with what I have. Ignore this. Now, I was saying that the E cell, there are several ways. You can look at it in terms of right-hand side, especially once you have a diagram like this. Talking about right-hand side, left-hand side is very easy. If you look at right-hand side, left-hand side is just okay. So we do have the right-hand side, left-hand side. And then at the same time, I talked about the cathode and the anode. I say the left-hand side is the anode. Right-hand side is the cathode. So we can just use the two calculation and you can see the value that we're getting is a positive value, positive 0.2. Baraka, your hand has been up. Let me give you chance. Yes, Baraka. Yes.
On the diagram, should you indicate the flow of electrons?
If you are asked, yes. But if you are not asked, it's not a must. Now, reason being, I'm always very particular about what you are answering. Reason being, if you are asked to do that, if not, don't. Because if you make any mistake, then examiners are always very good at looking at the mistakes rather than looking at the correct answers. So if you do make a mistake, then they will easily penalize you. So if you are asked, yes, but that's a very good question. And if the question is on the diagram, please don't show it outside. Show it, we have this wire here. This is the connecting where we have the voltage. So if you're asked on the diagram, ensure that you show it on the connecting wire here. That's a good question. Flow of electrons. Electrons will flow from where to where? Quickly. Is it cathode? This other side where we have zinc, I would say that one is the anode. This one where we have iron is the cathode. Yes, nodding. From where to where?
From the anode to the cathode.
From the anode to the cathode. Very, very correct. The most reactive to the least reactive. Very correct. And I've just said that if you are told to draw on the diagram, ensure you indicate it on that particular wire. Don't indicate it outside. Ensure it is on that. But answer that question if and only if it has been asked. If not, leave it like that. Are we together with question 2 and 3? I believe question 3, we did answer that. When we were starting, that is Roman 3, I believe we answered that. Then we can now look at this question together. In the production of aluminium from aluminium oxide, 100 amperes, I believe that was current, was passed for 6 hours and 40 minutes. Determine the mass of aluminium obtained if 1 Faraday is 96,500 coulombs, aluminium is 27. Now, there's a calculation which I want us to do together so that we don't waste time. So let us do this one together. First of all, anytime you're given this, by the way, one free mark, and let me say it's a free mark. One free mark is usually calculating the charge, the quantity of charge. That is normally a free mark. And we all know that that is free charge, the free mark. And how do we calculate charge? Charge is Q is equals to IT. That is the first thing that you're supposed to say. Q is equals to IT. Where I is the current time is, and T is time, and this time should be in seconds. 6 hours, like in this particular case, we're going to have 100, the current that has been given there is 100, but at the same time, that what we have there as the time is 6 hours and 40 minutes. Maybe you can see how many minutes are those? 6 hours. That is 6 times 60, that is 360. Plus 40, those are 400. Okay, so we can have something like, we'll have something like that. So this is 100 for current that has been given there. 400 is 6 hours and 40 minutes. Converted to minutes will give me 400 minutes. And then remember, this time should be in seconds. So we'll have times 60 to change it in seconds. That is what we'll have. So in this particular, let us analyze this one by one. It simply means that in this particular question, what we have, the charge that was used in this particular production of aluminium oxide, the total charge that was used is 2 million, let me say 2.4 million. The question is, determine the mass of aluminium obtained. But then we now have here 1 Faraday is 96,500. One important thing that you're supposed to know is during production of aluminium ions, how many electrons do we use? We all know that aluminium is written as Al3+. Al3+. Now, this 3+ here, the 3+ here is very important because this is what gives us the number of electrons that I'm talking about here. This number of electrons are very important. That is something that you're supposed to know. So this is a point that is very important. We look at this and we say, just 1 Faraday from what has been given. That 1 Faraday is equivalent to 96,500 coulombs. But remember, if we have aluminium ions, what we are going, the total number of electrons that we're going to have, is not going to be 1, but we are going to have 3 of them. So we'll have to look at what about if we do have 3 electrons. So this one is just equivalent to just like 1 electron. So here we are going to cross multiply 3 times 96,500. Give me the total charge that will be there. Give me the total charge that will be there. Give me the total charge that I will have here. Oh, Nyamache, what will I have here? Nyamache, what will we have here? Nyamache is not speaking. Nordin again. Nordin, what do we have here? Am I not giving the microphone? Yes.
289,500.
289,500.
Yes.
Like that, coulombs.
Yes.
So this will be the charge. So this will be the charge that will be used or that will be required to deposit 1 mole of aluminium, because 1 mole of aluminium has 3 electrons. Then you're being asked to determine the mass of aluminium obtained. Now, this mass of aluminium obtained, what we are going to say is, remember the total charge is this one here. That one is now the total charge. But then for us to deposit just 1 mole of aluminium, this is what we do have. So we can say this charge that we have here, this one, the standard, which is 289,500. This one here is used to deposit the mass of aluminium. And in this particular case, you've been given the mass of aluminium as 27 grams. Of course, that is the RAM of aluminium. Then you're being asked, this charge that we do have here will deposit what mass of aluminium? I want to believe that you can see that this one is almost like something that you're not calculating. This is something that is almost automatic, because we know that the Faraday is normally does not change. 1 Faraday is 96,500. We know that aluminium is 3 positive. So the number of electrons there is 3. We get the total number of Faradays there, we'll get 289,500. So this 289,500 coulombs can be used to deposit 27, which is the relative atomic mass of aluminium. So if this 289,500 can deposit to 27 grams, what about this one that was used, the 2.4 million? Just take a minute first of all to do it. Then once we get an answer, we'll do together. Do it and then you give me an answer. Yes, backbencher. Your hand is up. Please, if your hand is up, you raise up your hand if you have a question. If not, and if I give you a microphone, you have a question, please ask or comment. Michael.
Hello, Chair.
Yes.
I wanted to ask concerning, can you scroll up a bit, please?
Yes.
Could you please scroll up a bit? I wanted to ask concerning the 100 times 400 times 60. Where does
This
the
one
60?
here, yes.
The 60, where does the 60 come from?
This 60.
Yes.
Okay, thank you. We've just said that from this formula, Q is equals to IT, where I is current, T is time, and this time is in seconds. The time is in seconds. Let us take note of that. The time is in seconds. All of you are students of physics, so I believe that this formula is not new. In this particular case, we've been given the current of 100 amperes, which is this 100. Then you've been told is 6 hours and 40 minutes. So 6 hours and 40 minutes, if we convert it, it comes to 100 minutes, because 6 hours, that is 360. 360 minutes. If we add 40, it becomes 400 minutes. But then this time should be in seconds. That is why we are multiplying by 60 to change this time in seconds. I believe I've answered your question, but I can still see some hands up. If you have a question, just raise up your hand. Okay. If not, please lower your hand. Thank you. So if you continue doing that, I can, this one, at least I wrote this one for you better. Production of aluminium ions, there are 3 electrons that are involved. I've explained that. 1 Faraday is this. The 3 of them will give you 289,500. Thank you, gave me that answer. And then we say this 289,500 is equivalent to 27 grams. This is the RAM of aluminium given. Now, this charge that was there, the one that was used, this charge, what will it be? So that is why we have that. If we do have that, then we'll get our answer as 223.8 grams. Unless there is a question up to that. Thank you. If there's no question, definitions. How do you define a primary cell? Somebody give me an answer quickly. How do you define a primary cell? Or let me start. Okay, give me an example of a primary cell. Let us start with what we know then. Queenix, I don't know whether you are defining the primary cell or giving me an example, but at least your hand is up. Yes.
I guess I'll do both.
Okay, thank you.
Primary cells, these are types of cells which cannot be recharged. For example, the dry cell.
Very correct. He has given the definition, and apart from definition, he has also given the example, a cell that cannot be recharged after use. The dry cell, the mercury cell, those ones are primary cells. Once they've been used, and I believe you know that, of course, maybe it's this generation, but I believe you know that if you do have a dry cell, once it's used, you cannot recharge it again. Mercury cell, so those ones are now primary cell. Very correct. What of a fuel cell? So if there is if there are people taking notes, if there are people taking notes of something like that, I will always give you an answer. Fuel cell. I still have the Queen. I still have Queenix only. Any other person? Is it the only one who did good research? Queenie, seems like the floor is yours again.
Okay. Fuel cells,
Yes.
these are types of cells which convert chemical energy of a fuel directly to electrical energy.
Very correct. They
Example,
convert, example?
hydrogen oxygen cell.
Very correct. And he really did very, very good research. The fuel cells, they convert the chemical energy to electricity. Actually, that is the key word. So whichever explanation or whichever definitions we give, the keywords are just what he said. The keywords here, converting the chemical energy to electricity. These are the keywords. These are the keywords. Keywords, converting chemical energy of a fuel. The chemical energy is normally the hydrogen. Of course, where we have the hydrogen, oxygen, like the one that is the example that he has just given. Hydrogen, oxygen. The oxidant that is normally used there, I've written it as an oxidizing agent. That's the oxidant, is normally the oxygen. The fuel is normally the hydrogen, so it's being converted to electricity, something like the hydrogen cell. I believe also that one you did in class. Ra, really have good names. Yes, the floor is yours.
I had a question.
Yes.
So when you asked, okay, this is a different question, but when you asked the oxidizing agent and you're already given two half-cell equations, do you give the ion? Because the ion is one which is oxidizing, which is reducing, which makes it the oxidizing agent.
If you're given an equation,
Yeah,
that is just the question that we're looking at, the first equation.
yeah. So
And
if I
then
give
if you're talked about an agent,
the oxidizing agent, do you give the ion
yes,
itself?
no. Anytime you're asked about an agent, and let us know this, oxidizing agent, it is something in a physical state. It can be a solid, it can also be a gas or a liquid. It is never an ion. That is the agent. So like in this particular case, remember there's a revision class, so we can always go back and forth. So like in that particular question that we had up there, the oxidizing agent is Ag, that is silver in solid state. It is not silver in plus state, in ions, no. So the agent is always in physical state. So it can either be in solid, liquid, or gas. That is if you are asked the agent. I believe I've answered your question. A very easy question here. The reason for electroplating. This one you can even ask for ones, right? Oh, no, we don't have form ones, they're form twos. Yes, Ben. Papito, Ben, your hand is up.
It's used to prevent corrosion and rusting.
Correct. Prevent corrosion. Another reason is for what? Let me give another person. Hey, cappuccino. Yes. Another reason for electroplating. Do we really need to think about such? I've given you a microphone, please. Some of the names I can't read. Yes. Michael.
To improve appearance.
Very correct. And those are the main thing. And by the way, remember rusting is corrosion in ions only. So we normally prefer talking about corrosion. So like in this case, the reasons for electroplating, we can give two. Improves appearance and also prevents corrosion. Unless there is a question, I would like to put an end to question 1. Any question on electrochemistry that we've done so far? Electrochemical cell, some of the things that we've done so far. If not, let's look at the second question. Thank you. What is fractional crystallization? Another topic that students, very easy topic that students normally think is challenging. What is fractional crystallization? Somebody to give me this definition. Ryan, say something.
Fractional is the separation of miscible liquids with different but close boiling points.
Different but close?
Boiling points.
Boiling points, correct. But what he has defined is fractional distillation. He has given us fractional distillation, whereby you separate, and what is given is the condition for fractional distillation, whereby you separate two miscible liquids which have different but close boiling points, correct. Here the question is fractional crystallization. Anyone with something to say? Muya, Lawrence?
I think fractional
Yes.
fractional crystallization is the process by which two substances with close but different solubilities are separated.
Different solubilities are separated. That is correct. Now, in fractional crystallization, this is where two salts are separated based on their difference in solubility in the same solvent. So you put them in the same solvent, and then they have different solubilities in a given solvent. So at a certain temperature, another one will crystallize it. Then at a certain temperature, the other one will also crystallize. So this one is a method of separation, whereby you separate the two mixtures or the two solids based on their difference in solubility in the same solvent. I've given that the process of separating two or more crystalline solids based on their difference in solubility in the same solvent. So this one is very important. Solubility in the same solvent. Somebody's hand is up. Let your hand be up if you have a question, so that if I give you a microphone, at least, yes, Agent, your hand is now down. Okay, I've given the definition, so if at all you have your paper or at all you have something, you can jot that one down. Let's move on. The table below shows solubility of two salts A and B at various temperatures. Now, this is a very particular question, whereby we now have two salts. These salts can only be separated by fractional crystallization. So these salts are soluble. Allow me to move it to the next page so that we don't have a diagram that is split. So we do have the two salts. We have salt A and we also have salt B. We have salt A and we have salt B. Now, let us look at what is happening. Analyze this question first. Analyze what we do have first. What it means here, we have solubility at different temperatures. We have at 50 degrees Celsius and also at 20 degrees Celsius. Now, salt A at 50 degrees Celsius, it requires 86 grams of salt A to crystallize at 50 degrees Celsius. I'm repeating that. 86 grams of salt A is required to crystallize at 50. At the same time, 18 grams of salt B is required to crystallize at 50 degrees Celsius. Remember, we are talking about same solvent. Come to 20. 31 grams of salt A is required to crystallize at 20. 8 grams of B is required to crystallize at 20. So this is something that you're supposed to analyze first of all and understand what we need. It's a matter of seeing, do we have that particular mass that is required, like in this particular case, for this to crystallize at 50, there must be 86 grams. For B to crystallize at 50, we must have 18 grams. As simple as that. I'm really trying to simplify it in a simple layman's language. At 20, 31 grams of A. At 20, 8 grams of B. Let's look at this. A mixture of the salts contain 29.5 grams of salt A. Are you seeing that? Salt A, we have what? 29.5 grams of salt A. Definitely, even before I continue, and I'm doing that because I believe this paper was sent to you, so at least you had already read the question. So from this first point that we do have 29.5 grams of salt A. Salt A, if you look at salt A, we need what? 86 grams, meaning at 50 it will not crystallize. Because what we have here is 29.5, but what we need is 86, so it will not crystallize. Let us move step by step first of all. And then 16.25 grams of salt B at 50. For salt B, we need what? 18. But what do we have here? 16.25. Meaning, at 50, from what we've been given, none of them will crystallize. Let's now proceed. The mixture is cooled to what? 20. So let us move from 50 and come to 20. At 20, for salt A, we need what? 31 grams. But what were we given? 29. So it simply means still that this salt A will not crystallize. Let's go to B. At 20, what we need for B is what? 8. And what have we been given? 16.25. So definitely, if you cool this from 50 to 20, salt B is going to crystallize. And as it crystallizes, 8 grams are going to turn to crystals. So what will be the remaining mass? I want to believe that I've really done it in the simplest way possible. Determine the mass of the salt that crystallizes up to that particular point from what I've explained. I want to believe that we all know and we are in all agreement that salt A will not crystallize. Looking at the masses that have been given and the mass that we have here. The salt that is going to crystallize will be salt B. And it is 16.25, and what is needed for it to crystallize is 8. So the mass of the salt that will crystallize will be 16.25 that has been given. And then you subtract this 8 grams. If you have a question, I'm giving you just 1 minute, internalize that, and then we continue. Just 1 minute. If you have a question, you can also ask. I can see some hand up. Can see some hands up. Maybe I can start with Andrew. Yes, Andrew.
Yeah, can you please repeat the explanation
Yes.
that you just give? Can you please repeat the explanation that you just give? What you explain right now?
Okay, thank you. Tanvir, let me take all the questions and then see. Yes, Tanvir.
You said that salt A won't crystallize at 50 degrees because it has not reached the mass we have been given. Won't
Yes.
the 29 first of all crystallize and then to remain with the rest, or it doesn't happen like that?
It doesn't. It must be. If this one is to, if at all you're given here 100, then that can be possible because it is above whatever you do have. So always look at what is on the table, what is it, and then actually when it comes to solubility, it's normally a matter of reasoning out. So just allow me, but very quickly to repeat, or let me just get the last person here with a funny name. I don't know what Tralala is. The hand is down. Quickly, let me put it, and I'll still put it in a simple way, because right now you people are doing revision. No more speaking a lot. So let's look at what is happening here. At 50, we must have 86 grams of salt A. At 50, we must, and I'm using this word must, we must have 18 grams of salt. At 20, we must have 31 grams of salt A. At 20, we must have at least 8 grams of salt B. So these are the minimum, let me call them in a simple way, minimum requirements. The minimum mass that is required. So anything below this, even if it is 85, this salt will not crystallize at 50. Even if this one is 17 given, it will not crystallize at 50. So what we do have, sorry for that. Now, therefore, so after you've analyzed that as simple as such, just look at it as simple as such. Next, what we do, we look at what you've been given in the question. Like in this case, you've been given 29.5 of salt A. Let us look at salt A. At 50, it requires 86, so it will not crystallize. At 20, it requires 31, it will not crystallize. Then you just put an X to not. Let's go to salt B. You've been given what? 16.2. The mass, the minimum mass that is required for it to crystallize at 50 is 18. So it will not crystallize at 50 unless it is now pulled from 50 to 20. So if you go to 20, the mass required is 8. But then we have 16.25, meaning it can crystallize if pulled from 50 to 20. Because this mass, the mass that has been given, is higher than the mass that is. So the salt that crystallizes will be salt B. And that mass will be the mass that has been given here, 16.25, and then we subtract the minimum mass that is required for it. We get that. I believe I'm clear on that. If there is no question, let's move to the next question, that is question B. Explain how the use of ion exchange resins removes water hardness. I will just talk about it briefly, and then I don't know how you'll put it in words, but then where we have the ion exchange resins, that is where we do have sodium chloride. But we're now introducing the sodium ions. Now, when you're talking about ion exchange, the word ion exchange, I can even take you back to where you are writing maybe equation, how do you call the precipitation reactions, of course, whereby we now exchange the ions, exchange of ions. So what happens here is, we know very well that where we have water hardness, that is due to the presence of magnesium ions and then the calcium ions. Those are the ones that are responsible. And if you're talking about ions, it means it is something like maybe, for example, I'm just giving an example, magnesium carbonate, magnesium nitrate. So if we have an ion, it simply means that it is a solution. So when we have these ions, which is magnesium ions and calcium ions, these are the ones that are responsible for water hardness. Now, in the ion exchange resin, what we now have is sodium ions. So what happens in the ion exchange resin is these hard ions, the ones that produces or causes the water hardness, are exchanged with the sodium ions. So what comes out will be something like sodium ions and not the ones that are responsible for water hardness. I don't know which answer that you wrote. Anyone who did research or anyone who wrote something there to tell us what they said? There is no one. Quincy, your hand was up for 1 second. And then it's now down. But then, all in all, I can give you the simplest explanation. We have the calcium ions and magnesium ions are removed, or we talk about being exchanged. We're talking about ion exchange here. So we are saying they're being exchanged by, this one is just a word here, but typically it is normally the sodium ions. And these sodium ions are normally found in the dissolved sodium chloride, which is found within. If you can picture that diagram of the resin, of the ion exchange resin that you do have. If you picture that diagram, we do have sodium chloride inside. This sodium chloride is in aqueous state. It is dissolved sodium chloride. So you have the sodium ions and the chloride ions. So these magnesium ions and the calcium ions, these ones here, are going to be replaced or exchanged by the sodium ions. So what will be coming out of that resin will be sodium ions, but not this hard water, as simple as such. So the keywords, you have to mention the two of them because they're the ones that are responsible for the water hardness. You have to say that they're exchanged by sodium ions. Disadvantages of hard water, I think this one, I will not even look at that as such. There are several of them. We can talk about that. Wastage of soap. They can cause blockage in pipes, produces scum, any of those. If you do have a question, please ask. Selected this topic specifically because I know. Selected this paper because we know such topics. Very easy things. But at times students feel they're challenging. But you can see the way we are answering the questions. Please take note of keywords. Don't give a lot of explanations. Chemistry is all about just the keywords. Like in this particular case, just to give the ions that are responsible for, these ions that are responsible for water hardness. And then the sodium ions, just like that. State and explain the observation made when aqueous ammonia is added dropwise until in excess in a solution of copper 2 nitrate. This one is just you're adding aqueous ammonia to copper 2 ions. Give me an answer here. Give me an answer, someone to give me an answer. You're adding ammonia solution, that is aqueous ammonia, dropwise until in excess to a solution containing copper 2 ions. You don't even need to think about this. Since you've been in the lab several times, you need to just give me an answer here. I've given microphone. Yes. Gershom. You've muted again. Clement. Yes. Clement, the floor is yours. We can't hear you well, Clement, so I think I'm passing on the microphone to someone else. Hey. Someone called detective. Please let us not waste time if I give you the microphone. Please, I'm only giving the ones whose hands are up. So if your hand is up, I will give you the microphone. The question here is, just like in the laboratory, if you do have copper 2 ion solution, then you are adding, I told to add ammonium hydroxide dropwise until in excess. What observation will be made? Yes, Michael.
The copper 2 oxide partly dissolves in towards excess to form a blue precipitate, but in excess aqueous ammonia, the blue precipitate dissolves from a solution.
Very correct. Very, very correct. Normally in exam, so not in exam, but in the laboratory, if you add few drops of ammonia solution in copper 2 ions, you will see a blue precipitate. Then when you add now excess ammonia, you will see that the precipitate will dissolve to produce what? A deep blue solution. The precipitate dissolves to give a deep blue solution. So in this particular case, the observation that you're going to make is that if you add few drops, there'll be a blue precipitate. Then the blue precipitate dissolves to form a deep blue solution. And just like what he has said, the blue precipitate is copper 2 hydroxide. Then that copper 2 hydroxide, if you continue adding, or if you now add excess ammonia solution, then it will dissolve to give what we call the triamine. To form tetramine copper 2 ions. I think I've given that there. Unless there is a question. Somebody's hand is up. Please let your hand be up if you only have a question. Nothing beats. If your hand is up, let it be a question or something to comment on. Yes, I've given you a microphone. Now, unless there is a question, if there is no question, allow me to move to skip this question 3 because I'm looking at the time also. Question 3 is calculations. Allow me to skip question 3. I saw a question on salts here. Let's combine that one with this one for salt so that in the next class, we look at this other, there's this question for salts. I'm skipping that. I want us to combine the question that we've just talked about salt there, and then combine it with this question on salt that we do have here. I think it's question number 6 in your papers. Please turn to that. And then let us analyze this question. Let's analyze these salts. Because I'm looking at the time, we have like 10 minutes remaining, around 15 minutes remaining. We can analyze the question on salt so that once we are through with the analysis, even if you go back, when you now sit down and look at the paper, you can be able to answer the questions. Then next time we'll start on the calculation of moles, and if time allows, we'll continue from that. So I'm skipping and going to question 6. Let's look at question 6. This one is a question on salts. This is a question on salts. We do have a mixture, W. And anytime we have a mixture of a salt, then we add water and then we filter. It means one salt was soluble, another salt was insoluble. When we have a mixture, then we add water, then you filter. It means one of the salt was soluble, another one was insoluble. So this solution Y was the salt that was soluble. Solid X is the one that is insoluble. Okay, let's start with Y here. So this Y here is already the solution that is already the salt that is soluble. Okay, let's proceed. In this Y, we are adding lead 2 nitrate, then we are filtering. It simply means that if we add lead 2 nitrate to this salt, and we filter, for us to carry out filtration, it means there was a precipitate. Let us go step by step. It means there was a precipitate. And for us to have, remember this one is a solution. And from up here, we've already said that this one is a soluble salt. For us to have filtration here, it means we have a salt that is a precipitate. Now, it simply means that there was an ion exchange here. And what this solution Y contains an ion, which can be the cation or anion, but I believe it's the anion because this one's already lead here, that will form a precipitate with lead, telling you that this solution Y contains something that when added to this lead will form a precipitate. Which lead salts are insoluble? Quickly. Which lead salts are insoluble? Answers quickly. Let's save time. Let's save time. Which lead salts are insoluble? We need to know which ions are present in solution Y. And since we're having a filtration here, it simply means that there was something that was insoluble. My question is, which lead salts are insoluble? Ian. Ian, your hand is up. Ian is not answering the question. Have another one here. Chow.
Lead sulfate and lead chloride.
Very correct. Very correct. So we do have the lead sulfate. We also have lead chloride, because even the carbonate, but then we can have the sulfate and the chloride here. So it simply means that at solution Y here, we can either have a sulfate as an ion or a chloride as an ion. Let's proceed and see. Then we carry out filtration. And when we carry out filtration, we see a colorless solution and the solid. So this solid is what we're talking about. It can either be lead sulfate or lead chloride. But then when you add hot water, it means it dissolves. It dissolves. Which lead salts dissolves on warming? Which lead salts dissolve on warming? As easy as such, Joseph. There's several people. The chloride, very correct. Very correct. So it simply means that the white solid here is lead to chloride, telling us that this solution Y contains chloride ions. We still don't know the cation that is there, but at least we know that it contains chloride ions. That is why when that chloride ions reacted with this, we did have lead to chloride, which is here, dissolves on warming. Let's come to this other side. We have a colorless solution. When you add excess ammonia, it forms a white precipitate which dissolves to form a colorless solution. This one is normally just one ion. When you add excess ammonia, you get a white precipitate which dissolves in excess. Which ion is this? Which ion is this? Charles, Karemi.
Zinc ion.
Very correct. Very correct. You can see the way analyzing a flowchart is very easy. So it simply means that the cation that we have here is zinc. The anion that we have here is chloride ion. So solution Y is simply zinc chloride. Just like that. As easy as such. So up to that point, we are through. Solution Y, zinc chloride. Let us come back to the solid X. Solid X, there is a step 2 that is carried out here. This step 2, we get a white solid and carbon dioxide gas. Quickly, can somebody tell me what step 2 is? Quickly, quickly, quickly. Step 2, step 2. What is happening in step 2? Charles Karimi, only another person. What is happening in step 2? Step 2. Yes, Alan, what is happening in step 2?
Thermal decomposition.
Very correct. Thermal decomposition, not dissociation, it is decomposition. Meaning we are heating this. And if you heat it, you can see we are getting a white solid and carbon dioxide. The moment we are getting carbon dioxide, already, this one is a clue that the solid X that we have is carbonate, because it's only carbonate that will give you carbon dioxide gas. So one thing that already, at least up to that particular point, we have an idea that we have a carbonate, but then we don't know the cation that is present. We can still continue and see which cation is present. Of course, the carbon dioxide being a gas can escape. So this white solid, we add HCl, we get what? A colorless solution. We don't know. That colorless solution, we add a carbonate to get a white precipitate. There are several carbonates that are insoluble, so we still can't tell. But then, let's look at this step 4 and 5. Maybe it can give us an idea. In step 4 and 5, to this solution, when you add excess sodium hydroxide, it is sodium hydroxide, dropwise until in excess, you get a white precipitate. Which ions are likely to be here? You get a white precipitate. Now let us start with this. If at all it is excess sodium hydroxide, and then the precipitate dissolves to form a colorless solution, what will be this? So step 4, we have excess sodium hydroxide, white precipitate. Step 5, excess ammonia, white precipitate. Yes, these ones are giving us a clue. Somebody tell me which possible ions are present here. Victor, Baraka. Yes, Victor? Oh, Victor, you've disappeared again. Lemuel?
Magnesium.
Magnesium ion. Of course, he has given us the answer, which is correct. Let us now see. Let's quickly see how we are eliminating this. Now, remember, if we have a white precipitate which dissolves in excess, in excess sodium hydroxide, then it can be zinc, aluminium, or lead. It simply means that here where in step 4, those 3 are not there. Also remember, since we have a precipitate, calcium is not there. And at the same time, we are eliminating all the colored ions. The only thing that we are remaining with is magnesium. And in magnesium, if we add excess ammonia, we'll still get what? The white precipitate. So it simply means that solid X is magnesium carbonate. So magnesium carbonate, if you heat, you get magnesium oxide and carbon 4 oxide. Magnesium oxide, you add HCl, you get magnesium chloride. Magnesium chloride, if you add sodium carbonate, this one is now a precipitation reaction. You will have magnesium carbonate plus sodium chloride. The white precipitate will be magnesium carbonate. I want to believe that we are through with that. So at your free time, please go through the questions. I believe we've done almost all of them, apart from maybe the calculation that is there. But go through the questions that are under these salts and try answer all the questions. Some few minutes remaining, I'm giving that time for any question that is there. Andrew, your hand is up. Yes.
So, where you said magnesium, why not sodium?
Why not?
Sodium.
Why not sodium?
Sodium ion. Yeah.
Now, anytime we have the test for cations, sodium and potassium will not give us any precipitate. Actually, when it comes to sodium and potassium, the only thing that will identify the ions is the use of the flame test, whereby sodium will burn with a yellow flame, potassium will burn with a lilac flame. But then when you use the two, there is no precipitate. Actually, there's never observable change. Whether you're using sodium hydroxide, whether you're using ammonium hydroxide, there will be no precipitate at all. But remember here, if you look at it, there is precipitate Here also there is a precipitate. So sodium, potassium, those ones are eliminated from the word go. The only thing that you can be used to differentiate sodium and potassium is just the flame test. They normally show negative results with ammonia and sodium hydroxide. Any other question? Closing down the class. Shalala, your hand is up. Yes, somebody is asking. Somebody's hand is up. I don't know whether it is a hand up or somebody has just asked, why not zinc ions? Now, the place whereby we are eliminating zinc ions is in step. Even in step 5. Zinc ions, when you add excess ammonia, it will dissolve to form a colorless solution. Go back to step 8 and see that. It will give us a precipitate which dissolves to form what? A colorless solution. So in step 5 here, we have a white precipitate. If we have a white precipitate, definitely this one is not zinc ion. Any other question? We just have 1 minute left. Maybe I can take the last because of the time. So if I give you a microphone, please. The best quickly. Is not speaking. Ernest. Ernest. Yes.
What about aluminium?
What about?
Aluminium. Yes.
Okay, where we are eliminating aluminium is in step 4. In step 4, anytime we add excess sodium hydroxide, we will find a white precipitate which dissolves in excess. If it dissolves in excess, it's either zinc, aluminium, or lead. Which dissolves in excess, zinc, aluminium, or lead. But in this particular case, it didn't dissolve in excess. We had what? A white precipitate. So it cannot be any of the 3. It can't be aluminium, it can't be lead, it also can't be zinc. Time is up. The last person, the last hand up, yes? What is, yes? What is fractional crystallization? I gave that definition here. Now, time is up. I think we'll stop at that particular point. If at all you have any other question, we still have 1 more class this week. We'll start with those questions before we proceed. Thank you so much. Have a good day. Bye.